So you see my title, Relativistic Time versus Quantum Time, and what I claim is that relativistic time doesn't really exist, and quantum time doesn't really exist. So this is the relation between two notions which do not exist. So it's a special talk. So this is the scope, but I will have no time for everything. I will try to be pedagogic because I understand that many people here don't know deeply physics, and the first part of my talk will be concentrated on general relativity, and the second part will deal with the effects of these temporal effects in general relativity on quantum physics. Yes. So these temporal effects, they are what are called shifts, like temporal shift or spectral shift, red shift, blue shift, and so on. Also delays, time delays, which are known under the name of Langevin paradox very often. And these effects can have two origins, which are relative velocities, which mean more or less Doppler effect. And I will claim that a good appellation for that is velocity of time. I will explain what I mean by that. And the second possible origin for this effect is a gravitational shift, also called Einstein effect. And what is interesting is that these effects are predicted, of course, by the two theories of relativity, special for the kinetic or general for both effects, but they result only for two great principles, which are Lorentz invariance and equivalence principle. And in fact, special relativity is nothing but the consequence of the application of Lorentz invariance to the whole physics, and general relativity is the consequence of the application of both principles to physics. But what I mean is that only these two principles, without all the mathematical apparatus, suffice to predict these effects. And of course, they were predicted by Einstein before his general relativity theory was available, many years before. So there are many appellations for that, which are Langevin twins, time dilatation. And what is important, and I will present some points about that, is that all these effects which were predicted in the beginning of the 20th century are presently well confirmed on Earth, in space, in astronomy, and with a very high precision presently because of the use of atomic clocks. The precision now is reaching something like 10 to the minus 18, which is a really good precision. And when I will speak in my talk about perfect clock, I will not mean Swiss watches, but atomic clocks which have now a precision about 10 to the minus 18, which is 1 billionth of 1 billionth. And all these effects are verified at this precision, and of course in current life and even in simple laboratory experiments, they are not apparent simply because they are very weak, and it is impossible to detect this effect with a watch, even with a Swiss watch. But they are now very well observed with atomic clocks, and now we have reached a situation where they can be used as a tool. And for instance, I will present you rapidly an experiment where you measure temporal shifts, spectral shifts, which I call also velocity of time. This is the same thing for me, which can be used as a tool for altimetry, for gravimetry, for detecting water or metals or things like that, geophysics, prospection, and prevention. These effects are based on the clock hypothesis, which now is an observational fact. This fact is that two clocks do not measure the same quantity. If I have a clock in Paris and a clock here, or if I have two clocks here which are separated by a few centimeters, they do not measure the same quantity, and it is impossible, I mean at the precision of atomic clock, to synchronize them. This is really impossible. This is now something which is perfectly clear from experiments. And this is taken into account by the clock hypothesis, which was formulated by Einstein in the beginning of the 20th century, much before than this was apparent from measurements, because Einstein had no atomic clock. And the clock hypothesis is that a clock doesn't measure time, but a clock measures the proper duration of its own history. And this is at the basis of all effects I will present. And fundamental fact is that there are no other way to measure any temporal quantity. When you measure time, between quotes, with your watch or with any clock, you are measuring the proper duration of the history of your watch or of your clock. And if you want to read time, this implies that before you have put the right time on your watch, you have mise à l'heure, je sais pas. In French, mise à l'heure is just enter a time in your watch, and then the watch measures the proper duration and gives you the present time. So time and proper duration are two different things. And for instance, when you say it is now 12 o'clock, this addresses to an event, and the event is here and now. And when you speak about duration, duration concerns an history. I mean, my talk will have a proper duration of 40 minutes, for instance, I hope. And again, proper duration, it was a clock measures. So what is time? Time is something very different, because time is a notion which has to be shared. I mean, I want to say it is 12 o'clock here, it is 12 o'clock in Paris, it is 12 o'clock in the Andromeda galaxy, on the Mars planet, and so. So the way we have now to define time, which is not really a physical quantity, but is, I would say, a social quantity, is to choose a temporal function of space-time, which is a way to classify the events. And so we have a very wide choice to do that. There are an infinitely many ways which are not equivalent to define time, and they don't have physical reality, but it can be more convenient to choose universal time or atomic time or sidereal time or ephemeris time. They are completely different quantities, and no watch is able to read time, because time, for instance, if you take universal time is defined as the indication of one particular clock, which is one atomic clock in Paris Observatory. Well, in fact, this is not exactly that, because this is average over many clocks, but conceptually you can think that universal time is the indication of the Paris Observatory clock. And of course, you can read universal time only if you are in Paris and you are able to read the indication of this clock. So if you ask now, what is universal time here? How can you do that? You have to receive a signal which is sent from the clock in Paris Observatory. For instance, you receive a top which is sent every second by this Paris Observatory, which means every second in the proper time of the Paris Observatory clock. But you can yourself, using your clock, your perfect clock, you can measure the duration of between two tops. And of course, you will not measure 1 second, but 1 plus z second, and this is exactly the definition of the temporal shift, which coincides with the spectral shift. And this is why, if you have defined time as universal time in Paris Observatory, you measure the duration of 1 second of Paris Observatory of universal time, and you find this duration is 1 plus z second. So the temporal shift is z, and 1 over 1 plus z can be called the velocity of the time, the velocity of the universal time in this case, for me, from the observer at his position and his velocity. So this is very convenient to call that velocity of time, but if you call sidereal time, if you choose sidereal time, you can also measure the velocity of sidereal time and so on. So what are temporal? The shift I just mentioned is a temporal shift, and it can have two origins, kinematic origin, when you have relative velocity v between the source of the signal, which is a Paris Observatory clock, for instance, and me, and the shift is given by a formula which is in fact more complicated, but practically this can be decomposed as v plus v squared plus other terms which are very small. And what is interesting is that if you are not in relativistic theory, not in space-time, only this term exists. And the other terms are due to the fact that we are in space-time and not in space and time. And it is very important. On Earth, usually the velocity, the largest velocity you can have are more or less the sound velocity, which in unit of velocity of light are 10 minus 6. So you measure, due to this term, shift of 10 minus 6, but this would reach 10 minus 12. So it is very difficult to measure on Earth, but absolutely not difficult to measure when you use satellites, and I will show some points on that. And you have a second possible origin for the shift, which is a gravitational shift, also called Einstein effect. If the source and the observer are in a different gravitational situation with gravitational potential difference phi, then the shift is phi in c square unit. And most often, when you measure a shift, it combines the two origins. And for instance, when you use the GPS satellite, you have a combination of the two effects. And a spectral shift, which is often the way to measure a shift, is just a particular case of a temporal shift when the history which is measured is just one period of the radiation. So spectral shift is a particular case of temporal shift. And on Earth, since the gravitational potential on Earth is about 10 minus 9, a difference of gravitational potential should be a fraction of that. For instance, if you have two clocks at different altitudes, the difference in gravitational potential is 10 to the minus 16 per meter of altitude difference. And now, with atomic clocks, you are able to measure this shift even for few centimeters, about 20 centimeters difference of altitude. And I remember that the atomic clock precision now is 10 to the minus 18, so this is not very difficult to measure. And as I said, this is beginning to be used as a tool for gravimetry, prospection, and so on. So I don't want to go into these details, but this is just to explain you that in relativity, the true quantity is not really the velocity, but a hyperbolic angle. So maybe some of you don't know what it is, but this is not very important. But this can be taken as an explanation why there is a limit of the velocity, which is the velocity of light. Because the real physical quantity, which is the angle, the hyperbolic angle, can vary from 0 to infinity, but when this quantity reaches infinity, the velocity, what we call the velocity and what we usually measure, is reaching 1 in a unit of velocity of light. So the fact that you have limiting velocity in the velocity of light is a consequence of the geometry of space-time. And the Lorentz transformation formula that maybe you know and maybe you find very strange is just the consequence of the composition of velocity, which is in fact a composition of trigonometric angles, and it's just addition. So the Lorentz transformation is just addition, not of velocities, but of angles, which are the good quantity. Just I show you that just to explain you that the geometry of space-time, the relativistic kinematic is something which is very simple when it is expressed in a good way, which is as a geometry of space-time. So what are the shifts? I just want to show you this, this graphic. This is the word line of the emitter, which is in my which is the clock in the Paris Observatory, for instance. And along history, the clock is experimenting its proper time. And this is also an allusion to what was made before, because in general relativity, you don't have a time which flows, but this is space-time, and what happens in space-time, each observer or each object is describing its own world line from the past to the future. And this is another observer, this is me, for instance, from my past to my future. And so this is not time which is flowing for me, but this is me. I am flowing in space-time. And what I call proper time is just measuring the flow, my flow in space-time along my world line. This is like if I am on the road. The road exists as a world, but I can only be at some point of the road at a given moment. And I am discovering the road point after point. And I am living my world line point after point. And this is this succession that I call the flow of time, the flow of my proper time. But is that something really physical, or is that something only in my mind? We have no answer to that. And in fact, if we are living our life sub specie temporis, because point after point. But my world line exists as a wall. If you think about Victor Hugo, for instance, Victor Hugo has his world line as a wall from his birth to his death, but he lived his world line instant after instant. So we can now think about Victor Hugo's life sub specie eternitatis, but as everybody, Victor Hugo lived his world line sub specie temporis. So very quickly, I mention you this experiment, which was the first measurement of the Einstein effect in 1959, and this was measured on 22.6 meters of altitude, the difference between the receptor and the clock. And so the shift was only 10 to minus 15, and it was well measured, and after that it was measured with more precision. So on Earth, as I told you, the expected and measured shift is only 10 to the minus 16 per meter, and with the actual precision, this allows to measure this shift, or this velocity of time, if you prefer, as a measurement tool for measure altitude or for measure the presence of buried masses which modify the gravitational potential. And this is now becoming a tool, as I tell you. So this is modern, the most modern measurement on that, and this is interesting because maybe it's not on this slide, but they measured the effect only for altitude difference of 20 centimeters, and this since they use atomic clocks which are very robust and which are possibly transportable, this is becoming a useful tool. For the GPS system, this is a combination of the relativistic shift, which whose cumulative effect reaches about 7 microseconds per day. The gravitational shift, due to the fact that the satellites are on a high altitude, is about 45 microseconds a day. The combination gives this number, and if it is neglected, this means that if you think that the clocks on the satellites are measuring universal time, then you make this error, which is 15 kilometers per day, because 1 microsecond error is 300 meters. So this is something which is very important and very real, a very real effect. Okay, thank you. So in astrophysics, the shifts are very well measured, and for instance, the gravitational shift on compact objects like white dwarfs or the sun itself, I will not go into the details. In neutron stars, which except black holes are the most compact objects. And recently in 2020, and this was a Nobel Prize, redshift were measured for stars very nearby the Sagittarius A black hole. And since it was very near from the black hole, the gravitational effect was intense. The velocity was only 0.03 times the velocity of light. And this was the first time that the gravitational and the relativistic component in V square of the redshift was measured. So this is a very important measurement. So the conclusion of that is that this effect, which are effect of curvature of space-time, or the Lorentzian nature of space-time, are very well confirmed and very well understood. So now the point is, how can we make quantum physics in this space-time which is subject to these effects. So this is only a caveat because I will speak about interpretation of quantum physics, and you know that there is a school, a philosophical school, which claims that there is no need to make interpretations. We just take quantum physics as it is, and this is something which works very well and which is operational, and we don't need to make some interpretation. I would say this is an epistemic rather than realistic position. I will not adopt that. I will be in the frame of realistic interpretations, since gravity is something which has a real effect. So I think we need a realistic interpretation. So what are the points that I want to develop? As you know, there are many problems in quantum physics which require interpretations, and we have presently no accepted interpretations. So there are the superposition principle that we don't really understand what mean superposed state, intrication, non-locality, collapse. I will not go into all the details. And this is the same for Lorentz invariance between the usual quantum mechanics is not Lorentz invariant, and due to the success of the two theories of relativity, we really think that Lorentz invariance is part of the real world. It should also apply at the quantum scale. So quantum field theory is the Lorentz invariant version of quantum physics, but I'm not sure that this makes really the job, because it is impossible to reconcile quantum field theory with relativistic temporal effects, which are those that I mentioned in the first part. I will explain that. Also, as you know, gravity is not treated in quantum physics, and even more in the interpretations. There are some proposals that I will mention, but this is really lacune. So my claim is that it is mandatory to take these gravitational effects and the Lorentz invariance into account in quantum physics and in the interpretations. And there are some hints that this may help for the interpretations. And this is the position of Penrose, and also this is what appears in the Montevideo interpretation that I will present in some detail now. So my claim is that any proposed interpretation of quantum physics should include prescription concerning gravitation and the way it has to be included in quantum physics. For instance, the many-world interpretations requires a superposition of space-time, and superposition of space-time is an effect of quantum gravity. So you cannot choose the many-worlds interpretation if you have no quantum gravity theory, for instance. So the quantum field theory works in Minkowski spacetime, but in Minkowski spacetime you have no gravity, so you don't take into account these effects I mentioned, that's those temporal gravitational effects that I mentioned before. So in fact this is a fictional world because there is no gravity, and even if you have no gravity due to the kinematical effects, you don't take into account some temporal effects. So you have to adapt to the presence of gravity, and if you believe that general relativity is the correct theory, you have to adapt the quantum field theory to curved spacetime, and as I said, this possibly gives you a better understanding of of quantum physics, because this may help to solve some of these problems. So what I want to do now is to explore what are the effects of the temporal gravitational effect that I mentioned before. And these effects are at the basis of the Monteiro video interpretation. They are not considered as defects, but they are considered as real effects which are at the basis of this interpretation. And what they show, the interest of this interpretation, is that, as they claim, this may help to solve, for instance, the measurement problem of quantum physics, avoiding the problems of the other suggestion for solving these problems. And this is also at the basis of some proposed tabletop experimental tests that I will quickly present also. So I will not speak about Barbour. And there are many questions when you try to reconcile gravity and quantum physics. The first question maybe is, how does gravitate a quantum system? What contributes to the gravitational field? Is that energy density in weak field approximation? Is that the energy momentum tensor? But we have to define an energy momentum tensor, and when we try to do that for a quantum system, we have an expectation value which is infinite, though you cannot use this prescription for evaluating the gravitational effect of a quantum system. And there are many questions. What means energy for a quantum system? And there are many interesting, very unorthodox proposals in the literature. I will not comment on that, but I can give you the references. And this is interesting for our problem, because you have to remember that energy and time are conjugated quantities. So any property of energy should reflect on the property of time. In quantum field theory, the notion of particle is complicated, because in quantum field theory you have only fields. What is a particle? Is a superposition of different energy eigenstates, you can call that excitation, of a quantum field. And when they propagate in curved space-time, they suffer the temporal gravitational effects that I mentioned, and this may destroy the cohesion. So if you start with a superposition of eigenstates which are interpreted as a particle, when this superposition propagates on curved space-time, it may lose the possibility to be interpreted as a particle. So this means that particle could appear or could disappear in space-time. Just to remember what is the collapse problem, the measurement problem in quantum physics, which is a very important problem. It is predicted by quantum physics that the usual evolution, which is given by the Schrödinger equation and which is reversible, which is unitary, breaks when we make a measurement, and this is the collapse. And we don't know exactly under what conditions this collapse occurs. This is more or less the same question to ask as what is an observer. This is a big thing, a macroscopic thing. According to Penrose, this is related to gravity, but this problem is open. And there are also many problems linked with that I don't want to enumerate here. And a part of the solution can be what is called decoherence, which means that there are many degrees of freedom of the system which are not lost, but which are diluted in the environment. And this, the conclusion is that apparently quantum system becomes a classical system, but only apparently, because in fact it remains quantum, but the quantum coherence, the quantum correlations, becomes so diluted in the environment that we are not able to see them, and everything is like if they were really lost. But there is this new interpretation that I will mention now, which says that there are some particularities linked to the non-existence of time, which may better solve the problem.
Okay.
So I will not speak about Penrose, which is another explanation of the measurement problem linked to time. But what is the basis of the Montevideo interpretation is that the quantum to classical transition, which is more or less the emergence of the classical world when you make a measurement, is achieved via the usual and environmental decoherence, which is interaction with environment, which is something that is widely accepted, plus a fundamental mechanism which is due to the temporal effects I mentioned. And this is important to realize that there are different notions of time, because quantum theory is expressed as a function of a time parameter t, assumed to be some kind of classical time, which is a classical variable. But such a time doesn't exist, because if you are in relativity, the only physical notion is proper time. But if you have a quantum system, the quantum system is spread over time. You can think as a wave function which occupies a large fraction of space, and at each point of the localization of the wave function of the quantum system, the proper time is different. So you cannot assign a proper time to the system. You have to assign a proper time to each point of the localization of the system. So proper time cannot be used to be the evolution time. And what would mean quantum time? Quantum time is something which should be measured by a quantum clock given by some system, a clock, but no system is purely classical, so no quantity in quantum physics can be purely classical, especially when you are measuring tiny things which occur in the quantum world. So if you use a real clock, you are using a quantum variable t. I will not detail all the properties that this variable may have, but this is exactly what the proponents of the Montevideo interpretation do. And the conclusion is that a clock, a quantum clock, is something very special, which has, this is a collection of degrees of freedoms, which are different from the degrees of freedom from the environment. And the conclusion is that in the same kind of way that the environment can lead to decoherence, here the fact that you have a very special set of degrees of freedom which are used in the quantum clocks give a special case of decoherence, which is called gravitational temporal coherence. And in fact, this may be interpreted as the fact that we read the quantum clock, but the quantum clock is not able to give you a good information about the real time of in the system, which is a combination of the proper times of the various parts of the system. And the conclusion, for instance, what we mean. We speak about the state at time t, where t is what is given by the clock. It is called also the clock pointer. But a state at the time t, when t is this clock time, this corresponds to a probability distribution of several possible values of the evolution time, which will be real time, real relativistic time. And this is a cause of exactly what is called coherence, because even if the evolution remains unitary given by the Schrödinger equation, it doesn't appear unitary, I mean to the observer, which uses the quantum time, because of this uncertainty. Well, I don't want to comment more, but interestingly also, I have no time for that, but there are some tabletop experiments which are proposed to test the quantum nature of gravity, and this is linked. I will just show you the schema. And the idea is to have two particles on the left and on the right, and each particle is prepared in a superposition state with a semi-transparent mirror, for instance, which means that the particle can be at the same time on the left and on the right. This is very common, no problem to do that. This is made in the laboratories currently. And this is the same for the second particle. It is half on the left and half on the right. The point is that the experiment is prepared so that when the particles are very nearby, they can interact gravitationally. This is very difficult to prepare, but the claim is that in the next years this experiment will become possible. And what is the consequence? The consequence is that this half of the particle is not correlated to the other one, and this half is correlated via gravitation. So finally, the result is that the two particles become entangled, quantumly entangled, via the gravitational interaction. And if this is verified, this means, according to what is called the Locke theorem, I don't know exactly what's in Locke, but the Locke theorem claims that if you have entanglement via some interaction, this implies that this interaction is of quantum nature. So if the result of this experiment is positive, and this was claimed, for instance, by Rovelli and others, this would imply that gravitational is quantum. This would imply that, in fact, we have a superposition of space-time. I must mention that this theorem is discussed. I'm not sure this is really a theorem, because some people do not agree with that. But this is at the basis of many proposed experimental tests that I will not detail here. And now I turn to my conclusions with one L only, is that the temporal gravitational effect, shift and delay, have been shaken quantitatively and qualitatively at all classical states. They must be present at the quantum scales, and if not, we have to explain why. But we don't know how to formulate gravity at the quantum scales. So one question is what gravitates, and there are many differences between quantum systems and classical systems. For instance, it has been shown that the equivalence principle cannot be applied to the quantum systems, or it has to be at least modified. So we may have a quantum equivalence principle, weak equivalence principle in this case, but this is not done already. And what I claim is that both the quantum physics and general relativity cannot be considered as complete without answering to this question of harmonization of the temporal effect due to the curved space-time and the quantum physics. And clearly this is linked to the interpretations, and some interpretations are clear relatively to this question, and some are not, and I think they must be clarified regarding these temporal effects. And this is also related, of course, to the search of quantum gravity. And some tabletop tests may bring some answers in the next years and maybe refute some interpretations. Thank you.
All right. Sam?
I'm trying to understand this notion of quantum time.
Yes.
Just trying to understand it. So it looked like the way it worked was that you have proper time variables that are in superposition, and then the idea is that you have decoherence working on the proper time variables, which looks...
No.
That's not, okay.
We have no access to proper time. The only access we can have is through a quantum clock. So what is a quantum clock? A quantum clock, in fact, doesn't measure proper time, because a quantum clock is, in fact, a set of degrees of freedom. It is a macroscopic object. So, in fact, it is any observable, because any observable, you know that there is no time observable in quantum physics. So you have to construct some observable which will be your quantum clock, and this is a set. This is an observable which is constructed from a set of internal observables on the system. But since the clock, since the clock is not completely punctual, this is a mixture of different observables, and these observables are quantum observables, and they are subject to the uncertainty principle. So they give you a quantity which cannot be exactly time, that you try to be the nearest as possible to the proper time of the center of gravity of your system, for instance, but you have uncertainty. And this uncertainty is what is analyzed by the proponents of the Montevideo interpretation, and what they conclude is that this gives a loss of coherence, and the pure states, in fact, when expressed as an evolution with respect to the quantum time, evolve into mixed states, because in fact one value of the quantum time given by the quantum clock corresponds to superposition of states which would be expressed by the relativistic time. And this means that the pure states evolve into mixed states, or more technically, the off-diagonal terms of the density matrix go to zero exponentially, and the difference between a quantum state and a classical state is that in a quantum state you have off-diagonal terms which represent the quantum correlations, which represent the coherence of the system. If the system becomes classical, the off-diagonal term must be zero. If you want to be exactly classical, the off-diagonal terms must be exactly zero. Here they go to zero exponentially, and with a good characteristic to answer the measurement problem. And this is the fundamental point of that. And what is interesting is this is only the result of the application of the temporal effect I mentioned to quantum physics. There are absolutely no additional hypotheses in this interpretation. So even if you if you are not interested in this interpretation, this effect exists if you believe that space-time is curved at the quantum scale.
Can I follow up that? So what I'm trying to understand is what looks like decoherence on the relativistic time variables. So you said that it looks like you've got a superposition. Like you could describe this as a superposition of the relativistic time variables, but then it looks like you get back some kind of classical time variable later on, decoherence on the relativistic time variables. And I'm just trying to understand that notion of decoherence, because
Yes.
it looked like the way I think about decoherence is like random noise from an environment interrupting the system.
Yes.
But that can't be what's going on here, because the whole environment is the thing that looks like it's in a superposition.
There is a difference between this temporal decoherence and the decoherence by environment. Yes. I mean, the degrees of freedom of the clock are different of the degree of freedom of the environment, because they are really quantum. They suffer the uncertainty relations. So, and the degrees of freedom of the environment are considered as classical. So they are not quantum. And this is at the basis of all the mechanism. Am I clear?
Yeah, so it's a different kind of decoherence.
Yes, they are different types. Okay. And so this temporal decoherence is of different nature of the decoherence due to environment, and it is claimed by the proponents that it solves the problems of the measurement problem, which are not solved that by the usual decoherence, which are the problem of outcome and the basis problem. Yes, I have not gone into the details of that, but this is what they claim. And so this is really a progress over the usual decoherence.
Yeah, so many interesting things. I wanted to ask you about one that I have other reasons to be interested in. So this is not an approach I like, but I would like to know what you think about it. So you said that Minkowski spacetime, Minkowski spacetime, there is no gravity. Right? But there seem to be some approaches, flat-footed approaches to just say, take Minkowski spacetime, which is our spacetime, and then we add a gravitational field to it. Mm-hmm. So we disentangle gravity from spacetime, as it is in GR.
Okay,
I understand that this is a Weinberg's approach in his textbook. This is known as the spin to gravity.
This applies in a weak field approximation, for instance. Yes.
My question is, do you think that besides maybe the philosophical ugliness of this idea, purely on the physical reason, you think that there are reasons to expect that this would not work, so would not be able to keep Minkowski spacetime classical as it is forever, and just quantize the gravitational field on the side, and so never have.
So, if I understand, this would mean that at the quantum scale, this would mean that gravity is Newtonian and not relativistic. Because you would mean that if you have no curvature, you have no temporal effects. So this would mean now we know that we have temporal effects at scale of centimeters. What you say is it is possible that at quantum scale, which are maybe microns, you don't have curvature of spacetime?
Well,
this would be very strange.
I guess that if it is Minkowski, you still have what we call the kinematical effects, but in order to have the gravitational ones, you would have to explain them really as something about the gravitational field, which is not anything to do with the curvature of space. It would just be a physical field among the others.
Anyway, the gravitational I mean, the scale in the tabletop experiments would be centimeter scales. And at this scale, we know that we have temporal effects, I mean, engine shift. So if you want to explore the situation where you have no space-time curvature at scale of centimeter, this would mean that you have to reject general relativity theory, and you have to construct a theory which tells you that you have gravitational effect and space-time curvature at scales beyond centimeters, and no space-time curvature at small scale. I don't know any proposal like that. I don't say it is impossible, but this would be very, very curious, because this would mean that you should have a transition scale at centimeter or maybe millimeter or micron, I don't know. Well, I'm not sure, but here it is true that there is a focus on gravitational origin effects, but you have also the kinematic effects which are present, and I don't know in which extent such thing would also work if you are considering the kinematic shifts. I don't know.
Yeah, I will want to follow.
So you wanted, because I thought you were suggesting that we could get rid of curvature completely and have a false theory interpretation of gravitation.
That's the idea.
So then I want to press a bit Lorenzo's question. So Lorenzo, I want to ask you, what do you think of the idea of replacing general relativity by another theory or interpretation where you reinterpret curvature, you say space-time is flat.
Yes.
And what we describe as a space-time curvature
Is a field, is a spin to field.
Yeah.
Yeah.
But
Many people try to do that, but since Einstein, since Einstein, but presently there are no theory, such theory which works. But even if you have a theory like that, it should predict the temporal effects which are observed. So it should be indistinguishable from general relativity at the scale where general relativity has been confirmed. So I'm not sure this would make a difference here, except if there is some strange phenomenon at the scale of millimeter or centimeter, which tells you that this effect suddenly disappears. But such effects have been observed for elementary particles in cosmic rays, in accelerators. If you take the description of neutron stars also, they are taken into account. I'm not sure this will work.
All right, so please join me to thank Marc again.